like to acknowledge that I was brought onto this project only about 6 months ago. Celeste Ruian and Patricia Hubbard, who has left Sandia, both really started this project and did the bulk of the work on this project. I kind of came in and I'm working on this part, but 2 other parts which I'll explain in a minute. And Raymond Wolfgang also came on probably about a couple months ago. So what we're going to talk about today is requirements efficiency and some of the challenges and best practices that we've learned from going through the professional literature. And I'll explain where that fits in a minute. Next slide, please. Several of you on the call are not from Sandia. For those of you that don't know, Sandia is operated and managed by the INCOSE, or the National Technology and Engineering Solutions of Sandia, which is a subsidiary of Honeywell. We are a contractor to the U.S. Department of Energy, National Nuclear Safety Administration. For many of you probably know we work with nuclear weapons, but we also do work with defense systems, energy climate, and global security. Next slide. And I won't go spend too much time. Just for those of you who aren't aware, Sandia has been around since the 1950s. Our second site in Lawrence, Livermore was established in 1954. We have been around and have been doing various work in design engineering and support for the government. In the 1990s, for instance, we developed an advanced synthetic aperture radar that was used in Desert Storm. We also started piloting with the Waste Isolation Plan, or the WIP, which is in Carlsbad, New Mexico. In 2000, we had used some Sandia foam was developed that was actually used to neutralize the anthrax on Capitol Hill. And we most recently have rolled out glitter-sized photovoltaic cells made of crystal and silicon. And I just made this as a highlight. We've got a large brochure that's available on the public domain site that lists a lot of Sandia's accomplishments, so I won't spend too much time there. Next slide. Sandia has really 5 main facilities. The 6th one is actually one that we supervise. As I said before, we're located in Albuquerque, New Mexico, and in California. We also have a site in Hawaii, which I'd like to get to visit sometime, and it's our rocket launch range in Kauai, Hawaii. The waste isolation pilot plant we don't own, but we do support, and that is a site just east of Carlsbad, New Mexico. We have the Pantex plant in Amarillo, Texas. That is really one of our big testing facilities. Nuclear weapons are also dismantled there as well, and we look at how to handle the aging stockpile as well as a few other things. The site in Nevada is, again, a test range, and it's really more for development and test support. So that's just kind of a quick overview on Sandia. So the purpose behind this research was really the main thrust was try to find ways in which we can gain efficiency in systems engineering requirements management. By what do I mean by that? We're looking at efficiency in terms of time reduction while maintaining quality, but still reducing cost and schedule. And we wanted to understand, what are some of the processes that are in place, and how are these things inefficient, but also what are some of the best practices that are in place, and why are they efficient, and how can we adopt them? So there are 3 prongs to our work. The first one was a literature review, which I'm talking about today, wanting to look at, what is currently out there in the literature, what are they teaching, what is going around, and, what are some of the best practices. But additionally, we wanted to benchmark what's going on internally to Sandia. Where is Sandia ineffective or inefficient? Where are they efficient? What are the processes and practices in place? And on top of that, we're also benchmarking externally, wanting to look at the best practices for larger corporations like Boeing and Siemens and a whole bunch of others. And we've actually been working on that kind of all at the same time, and we'll be releasing that document internally to Sandia in a little bit. So the part I'm presenting today is really just on the literature, but it's really the findings from there seem to be very similar to what we're finding in the other 2 areas. So on to the next slide. When I had this reviewed, somebody had said, well, what do you mean by requirements? Well, in model-based system engineering, you hear about the standard engineering V. And part of the V is looking at the system level and subsystem level requirements, taking these requirements and then linking them to system verification and validation plans. Part of what you do when you come up with a concept, you have to come up with those requirements to help spec out what it's going to be before you can actually design and develop it and test it. So this is that we're going to be talking about is that formalized approach of systems requirement. Next slide. The articles that were pulled up for us were reviewed over 65 articles, although I can tell you we have several more in our database that we've added, and they really have not added any new findings of the same things that we're seeing here. But they're mostly from journals and peer-reviewed references. Recent publications last 10 years, some conference publications. These were highly relevant. I'll give you a breakdown of journal conference proceedings. We found that the majority of the articles really looked at requirements management in general, although there was really an equal number, and I'm sorry I don't have the 13 circled, on general and validation and verification. So the general requirements overview and validation and verification is what most of the articles were addressing. Next slide. The next couple of slides, what I want to do is go over the really top level findings that we found. And these things we did present to the Sandia working group on requirements, and they were kind of surprised by this. But the big things we found were, and I hope if I spend too much time on this, please forgive me, is that you want to avoid these big requirements up front. What do I mean by big requirements up front? These are these large, detailed requirements that develop from customer interactions and source documents early on. And a lot of times it's in the waterfall approach where you go through and work out all of those details up front. Let's generate all this documentation, pages and pages and pages and pages. The problem is sometimes it's hard to think through some of the iterations or ramifications of your design until later on, so you're going to have to go through and make changes. And you're less agile in that process. Additionally, you're really more likely to over-engineer. So one example is the graph that you see on the right of a successful software program that came out, and it looked at how many features do the customers really use when that product gets out to market. And they found that 45% of the features were never used. So even though they developed it and spent it and it worked, 45% were not used. So this was one example of saying, gosh, we worked through all of this, we said we have to have all of these things, but really, perhaps time and money could have been spent elsewhere. We also know that when you start to go through this big requirements up front, the changes later on are much harder to make, more difficult to make, and more costly to make. Because now not only do I have to go through all of these sub-processes, I've got to go from the sub-process to the sub-process to the process and up higher, so that one change at the bottom of the document can have multiple changes as things are connected later on. Next slide. The other finding we found was front-load the requirement process. And this may seem contradictory to these big requirements up front. But really what it's saying is you want to focus resourcing up front to cover requirements capturing and design and validation, but only for these critical requirements up front. Those items that are critical to the technical performance and support critical operation needs and of the particular system you're doing. So let's say I have to develop a system that has to travel X miles an hour and has to cover X distance. All right, that's a critical requirement. But saying, gosh, and it needs to also support English and French and some of these other things, and well, that may not be as important right now. So really wanting to look through and say, what are these critical requirements that we need, and focus on these. So you're shifting it by putting this resources up front early. You're bringing these test engineers in, you're bringing the designers, the stakeholders in to say, all right, you said it needs to go this many miles an hour. Help me understand what that really means. You know, what are those parameters? How am I going to know it? How am I going to test it? How am I going to verify it's doing what it says it's going to do? And so by doing that and getting these things laid up front, you're going to save time and effort later on. And I'm going to go through that in just a little bit more. Next slide. So kind of doing a quick comparison, and this chart was just sort of put together and saying, what are the differences between this big requirements up front and this front-loading or critical requirements up front? With requirement elicitation, when you're doing it with the big requirements, you might have the customer or the requirements team is going to say, okay, now I'm going to work on this part. It needs to go this many miles an hour, which means it's got to have this and it's got to have that. But if I'm bringing in designers and test engineers at the same time, they're going to start saying, well, but I really need to know what some of these parameters are because we've got to test it. And how are we going to test it? And what are some of the metrics? What are some of the measures we're going to do? Additionally, if you can do this front-loading process, you're really supposed to be delving down and doing things in parallel. In other words, I may have some experts in one particular process or function, and I'm going to say, you work on taking these and decomposing them and getting them down to the specifics. You work over here and you work over here, rather than having a requirements team kind of do one set, then another set, then another set. So by doing it in parallel, you should save up time and effort. And also for requirements management, you're going to get a lot of detail doing it doing the rough approach. But when we're focused on the front loading, you're really going to focus on just those things that are critical, with more detail later on coming on. For derivation and decomposition, by that is a lot of requirements may be implied. In other words, I need to say it needs to do X, and so the requirements team is going to say, what does that mean? Let me break it down. Let me try to figure it out. And they're going to have to go through a lot, which might be implied. And so they may start making assumptions that may be erroneous. But by doing it with the front loading, the key stakeholders and everyone are going to be there with these critical requirements, breaking them down to make sure that these are not implied and these are not erroneous and these are exactly what we need. And for validation efforts, when you're doing the big requirements up front, you're really not talking about validation. You're just going to do it eventually when you go through the review process. But really with front loading, they want it to be done ongoing. Somebody have a question? I'm sorry. Additionally, the important distinction is that verification. So when you're doing the requirements up front, they want you to link to that verification methodology. How are you going to test it? What are the parameters you're going to use? How are you going to know that you've met those parameters? And that is set for those critical requirements up front immediately, as opposed to, well, I just know I need to test it, and it'll be, something. Next slide. So some of the main findings with front loading, as I think I said before, is that you're going to be using that concurrent requirement engineering. So you're going to do this frequent kind of coordination back and forth. You're going to get that parallel flow down. And you're going to have kind of a standard procedures for how that they are going to be engaging and breaking down from these higher levels to these lower levels. And even though you're investing a lot of time up front, it's really a lot cheaper to bring in engineers to do this design approach than to bring them in at the end and have to redesign things. So it's a lot easier when I'm in that design process to physically test something and say, oh, it didn't work. Now we got to go back and retest it and redesign it. So even though it seems like a big investment in resources, let's get this done. Let's get it done up front. It's going to help to limit the resources and reduce the expenditures or excess later on. Some of these things with critical requirements up front means you really have to link to those measures of effectiveness and those key performance parameters. What does it say it needs to do? What is that really going to be? What does that mean? Not just, well, it has to work well, or it doesn't have to have any errors, or, has to be easy to use. That doesn't mean anything. So really trying to say, what does this mean? And so by doing that, you're going to speed up this flow down of information, and like I said, it's going to be cheaper cost-wise and save up on timing eventually. Next slide. Another main finding we found is that change is going to occur. No matter what you do, you have to anticipate that you will have changes in requirements. And changes in requirements really are going to occur primarily in that beginning time when you're conceptualizing the idea of what you're trying to develop. They say probably between about 20 to 40% of all requirements change initially during that conceptual phase. And then as you go through the different phases, they tend to wean down a little bit. And there's a lot of reasons for change. Some of them are not all bad, but it may be things like the customer changed their mind, the testing parameters we're doing, we can't have certain things available, the capture was not correct, so we need to modify it. And you may not just be changing something, you may be modifying it, as well as just additions and removals. And what you can see across the bottom right chart is looking at cumulative changes across the software product versus additive changes. So the cumulative, you can see with the number of requirements added, it goes all the way up to, 180 requirements from 40 initially, versus you can see the bulk of them really are in the conceptualization and development timeline. And so those are the three main findings. What I'd like to do now is talk about some of the larger areas of the requirements process in terms of what the literature is telling us. And some of the things it's saying is there's a lot of challenges in requirements management. And part of it is saying, why? Well, establishing adequate requirements What is an adequate requirement? We've gone through some documents where people might say, here's a requirement, we've got 6 different parameters, it says it needs to do X, but now it's not really linked to what it needs to do, how it's going to be tested, how we're going to verify it, and so they need to really be adequate. A lot of times we find that the requirements engineer may not be an expert in that domain. They may be a really good requirements engineer, a really good system engineer, but they may not be an electrical engineer or a composite engineer or a manufacturing. And so you need to take that into consideration. Communication tends to be a real problem, inadequate communication. A lot of times we found in literature of people saying, we're communicating via documentation. Hey, review our program, look at our requirements management database, and it'll tell you what's going on right now. We're just following that. But communicating via documentation is not communicating. And so you need to really communicate. And, of course, unstable requirements. So some of the best practices are, again, avoiding the big requirements up front, good communication. But some of it is also consistency and uniformity. And by that we mean by developing a really good requirements plan on how these requirements are to be maintained and traced from the customers all the way down to lower level requirements. How are they allocated, managed, updated? Let's get that plan in place and be consistent throughout the entire project. Looking at requirements management tools. Doors is an example, the IBM Rational Doors. There are a lot of other tools out there. I know Sandia primarily uses Doors, and we're trying to find out what some of the other companies have been using, and there's hundreds out there. Some of the other things we found is that there's actually requirements management tools that can really help you in terms of consistency. There are drawing tools that will actually take your drawing, put it into grids, and say at A1, this is what it says, at A2, at A3, at A4, and it will convert a chart or a graphic actually into specific requirements with each particular grid of what it needs to do. They exist. There's language parsing tools. They can take documents and help you parse it from the natural language and make those into requirements that you can then review. So there are a lot of tools to do. There's common taxonomies that can be done, such as CBOC, and those also help.
Just what? I'm sorry.
CBOC?
Oh.
Yeah. Sorry. Systems engineering, yeah, of course. Yeah. Sorry. I talked down, I apologize. And another thing to keep track is really to look at these requirement tracking metrics, things like count, volatility, traceability. Do I know, am I able to count the linkages up and down to where these requirements from? Can I say where this requirement came from? And how is it linked to something else? Where does it come from? And I'll get to some of that in a little bit more regarding that, but it's really laying out a really nice plan up front of how you're going to document these requirements, what kind of parameters you're going to assign to them, how you're going to validate and verify them, and stick with it throughout the entire process. Requirement solicitation. There is no perfect method for requirement solicitation. Matter of fact, there are many, many different methods exist. But the point is trying to identify what is the best practice and best method for the system or for the tool or for whatever you're trying to develop. You may end up having to use a combination, and that works fine. It may be let's sit down with these stakeholders, we'll do some interviews with them, but now let's sit down with some of these engineers and take some of their drawings and go from there. Let's sit down with some of the test engineers, and you can pull from different methods to do that. But the best thing to do is to say, let's develop a plan for how we're going to gather all of these requirements. I need to look at requirements for these specific functions or sub-functions. I need to look at requirements for this particular interface. I need to look at requirements for however you're going to be in testing, whatever, and then develop a plan to ensure that you're going to be gathering and getting all of those. You want to ensure proper stakeholders are there. You can't just have the requirements engineer sitting in a room brainstorming and coming up with all these requirements. It's not going to work. Even though you may not want the test engineers there, it's probably pretty important to have them there up front. Agreeing on prioritizing requirements through verbs or priority levels. Some things are going to be more important than others, are critical. Let's say that. This is a critical requirement. How are we going to identify this requirement is higher priority than another requirement? For instance, you want to identify interface requirements. It's not just saying, I need to be able to tell the system it has to go X far and use X metrics. It's what are you putting into the system? What are you getting out of the system? And you need to specify it from both sides. It's important to think about that. and defining what those inputs and those outputs are going to be. And who owns the interface? A lot of times we found when we were going through some of the system requirements that nobody really knew who owned them, who owned the verification process, who owns them. You've got to be able to say, this person developed it, this person owns it. Study existing systems. A lot of times you might be able to say, we can use this navigation component from an existing system, but we can make some of these changes to it. So you might be able to actually utilize existing requirements that have been developed for other systems that you have. Sometimes we can't do that, and we're going to have to do modeling. So we may just come up with the best modeling we can to say how is something going to perform under certain parameters, and you can use various modeling techniques to help you gather these various requirements to see how it's going to perform under different circumstances, different situations. And again, using standard formats and templates is really very helpful. We talked to several people externally, and I can tell you some people will say, gee, at my company, we have 12 different parameters associated with every requirement. Another person said, we have 60. Another person said, we have 5. We have this. And sometimes they said, we don't know, but people would call the same thing different names, and then you're trying to go through these, and you can't reconcile, and you can't figure out what's going on. So if you can set and establish a standardized format that you agree upon that works for you, and utilize that throughout the process, it's going to save time and effort a lot later on. And Sandia's not the only one who has problems with this. So another thing to think about, too, is prioritizing requirements, especially things like safety and efficiency. So requirement specification, just as I said before, what are some of the standards that you want to link to these different, or I guess metadata that you want to link to each of these requirements? But additionally, you need to avoid inconsistent, ambiguous words. Things like, it shall do this. It should perform at least this rate. It will at least go between X and X, but you need specifics. And they said it's so full of words of shall, might, will. You need to really be consistent on what that means and establish it firmly. Separating needs from solutions. I need it to go this does not necessarily mean does it have to go this and why. And writing requirements with a sound verification pathway. In other words, I've got this requirement, it shall be user-friendly. What does that mean? And how do you verify that? It doesn't mean anything, right? So trying to be saying, what does this mean? So one example is looking at this mnemonic that we found that several people referenced was called SMART. To say, is a requirement specific, measurable, attainable, realistic, and time-bound? And that's actually a nice mnemonic to kind of follow and to think about even in terms of the metadata that you might be attaching to it. And you really want to make sure that you avoid redundancy with systems. It's not uncommon for you to separate software and hardware, go down and start writing different requirements, and in the end find that they overlap in certain places, and now you have redundant requirements. The worst part is they're redundant, but they may have different wording, terminology used, different measurements attached to them, and now it gets to be even more confusing. So take advantage of patterns, standards. In other words, if you can take your project and set up what those metadata might be and kind of be consistent across, that's a good way to do it. Again, I think I mentioned using some of these automation tools, which will help you parse existing documents or graphics into them. You want to make sure you couple your verification testing. How am I going to test it? How am I going to accept it? How am I going to know it met the requirements that I want? You know, let's write this and spell this all out. Also make sure that you assign responsibility. The problems we don't know is you've got multiple people who can come in and make changes, author, add, remove. Maybe it's better to have kind of a consistent person that you go to so that when changes are made, they make sure that the parent and the child are changed and there's consistency going through in the document. And sometimes they mentioned that if you have a component that's something that's commonly used, you might be able to pull from that in terms of the requirements for it. So maybe you have a certain button that's going to press and do certain things. It'd be great if you could just pull those requirements from something else, borrow them, and plop them into your document. Right now, at a lot of companies, you can't do that because they use different tagging, different methods of doing it, and have different ways of recording the requirements. Can you hear me?
Oh, yeah.
Okay. Next one. improving requirements derivation and decomposition. Derived requirements are those that come straight from the customer or stakeholder, but they're inferred or derived from the stakeholder's requirements. And in other words, there's a high level there, but now you actually have to figure out what are the different constraints and considerations and things that are implied in it. Because the customer may say, I need you to build a system that's going to do X, and it's going to go this, and it's going to be this effective. What does that mean? Now I got to figure out what that means. Well, it's a thing that's got to travel in the air. I've got to think about all the flight dynamics. And so here you are having to go ahead and make all of these assumptions. And if you do that without the customer present, you may say, oh, no, we wanted a helicopter, not a missile, or we wanted, I don't know, just an example. So requirement derivation is really highest in its earliest stage because that's when you're trying to work out all those details. That's when you're trying to say, from this concept, what is this physical design, what is this physical thing that we're going to be developing? Additionally, they may be not explicit. They may just have kind of some constraints to them, and so now you've got to work out what are those explicit test cases. What are the explicit environments it has to operate in so that I can put those in terms of parameters and extremes to make sure it's going to handle all these things. Sometimes the customer or the stakeholder may not think about some of these details, and so you might have to bring them along in the process to work through them. One of the problems we find is non-functional requirements may receive less attention, but they may be important. It may not be something that's going to be how it's going to fly or how it's going to maneuver, but it could be something with, how it's put together or what components it's made of. Maybe I didn't specify it had to be all metric components when it needed to be U.S. Components. And requirement decomposition, as I'm breaking these requirements and coming them down, can lead to more flow-down errors. So if I do something and derive it up front and make an assumption, now that assumption is percolated farther down through my requirements, and oops, now I got to go back up and change them all. So it can be an issue. And designers and engineers, as they work out the design, they may tend to estimate requirements or base it on, I think this is more important than things, or they may skip steps as they go along the way. They may place prioritization on things that I know this is really important on the last project I worked on. So therefore, let me put a lot of attention on this type. And that may not always be the case. So you need to think about how things are going to be further refined and have someone there in the process to go through and make sure that you're evaluating each of these so that you can derive these requirements consistently up front. So the next slide. So when you're deriving these requirements, you need to make them explicit, and you need to subdivide by functions or elements. And you need to plan sufficient time for deriving these requirements. They may be hard to operationalize, things like maintainability or supportability, or they may be subjective or qualitative in nature. And that's kind of hard to do. What do I mean by something's maintainable or something's supportable or something's going to last 10 years? What does that mean? How do you kind of come up and quantify that and come up with specifics for it? And sequencing and separating these requirements into these steps in terms of how one behaves from one state to the next is important. So I may have a toggle switch, and on it does one thing, off it does another thing. Or maybe it's a three-way switch. And you have to make sure you get each of these states, and you plan out each of the different requirements going through each of these different states. And you really want to make sure that you think about what are those key performance parameters for these requirements. You want to watch for duplicated requirements, as I mentioned before. It's very easy for you to say, cut and paste, but it could be something different. And it may be that I've duplicated it now and I don't find out till later on. Parameter mismatch. It's not uncommon for me to say something in units, in centimeters, and someone gives it in inches, or weight in grams versus pounds. Dangling requirements. I have a requirement, but I have no parent to it. I don't really know where it came from. It's a standalone requirement. Is it truly? It could be. It's possible for it to be a completely standalone requirement. Probably not, but you need to make sure where did this come from. Again, you may have child missing too, so it may have a requirement, but then there's nothing there to help you understand. How are you going to link it? What are you going to test it to? What does it mean? And then making unwarranted assumptions, which can tend to creep in over time as you're going through these. Next slide. If you remember, initially I showed you the systems engineering V approach. The W model is one that's been proposed a lot, and what the W model is it links in this testing up front as you're going through each of of the requirements. So I develop my requirements, I may have assumptions about my requirements for my tests, my sub-requirements, and at each point in stage, I go and link into how each of these things are going to be verified and validated coming in. And so that way I can assume that I'm going to be able to make sure that these are valid, verified, usable requirements in the end. Some of the requirements that we find difficulties with validation and verification is really understanding what some of these extreme loading environments are going to be. In other words, what are some of the test cases that I may have to operate it in? Can I even know what's going to happen at, 600 degrees centigrade? I have no idea. Can we test it? Can we do that? And so you need to think about each of those different extreme situations that can happen. Does it have to travel over a road for 100 miles of distance? Can it bump? Can it move things? An inadequate test review of the test cases. In other words, how am I assuming that I'm matching each of these testing up to each of the requirements? I may have just said, we're going to test it in the test chamber and that'll be done. It doesn't really tell me what kind of test. How am I going to test? What am I looking for? What are the parameters? Really trying to link that too. One of the other things we have to watch is a similitude to other designs. Thinking that, gosh, it's similar to all these other systems I've worked in, but then not realizing all these other things can creep in. I may be, for instance, we're talking about developing software that might work over the internet. Well, the internet is changing rapidly. So something I may have developed a year ago probably won't work as effectively as it would now. So really having to keep on the touch of understanding that you need to think about the new environment that you'll be working in. And it may be an environment we can't even envision. So, which is part of the issue we're having with, a lot of systems are having with thinking about autonomy, self-autonomous cars. Wondering, how am I going to get these systems to work now, and how am I going to get them to work in the future, when it may be a slightly different setup in terms of how the roadways are constructed. So, what can we do for validation and verification? In other words, validating how is it a legit requirement and verifying that I've met this requirement. I've tested it, I've verified that I've met what I said I would do. Some things we can do is rapid prototyping, and it's good. Useful early on, so I can kind of do it quick and dirty. Assuming lots of communication with the stakeholders is really important. You want to make sure that you're consistent, you're complete, you're reliable, realistic, and that all of your ones you set out are traceable and the data can be captured. It's really important. Review your all requirements, including your validation and verification. Include multiple organizations, your designers, your stakeholders, your test engineers, your other kind of mechanical engineers, all these people that need to come in, not just the requirements engineers. Confirm traceability of all requirements. This includes maybe using a matrix for it, so that you can actually trace back and say, where do they came from? What do they mean? Why am I wanting to do this? Who said I'm going to do it? Who's responsible for it? It's time-consuming, but it's necessary to do that, especially throughout, the life cycle of things can be changed. Additionally, you want to ensure you have full test coverage, and you want to identify and quantify the limit states or constraints. It needs to work in X, Y, and Z environment, but not, P and Q, or this, but be very specific of what that means. And by structure, augmentation, or insurance case, and I'm sorry about the terminology, what that really means is that you have decided, who is going to capture that information, who is going to document that information, and how you're going to provide that information to verify that that requirement has been claimed or has been verified. In other words, how are you really physically going to lay it out? So this requirement is now going to go to these test engineers. They're going to run this test. They're going to capture X data. This data is going to be between these parameters, and this is going to come back to say, yes, I now have my assurance case that my requirement's been met. Slide. Managing changes. As I said before, changes occur rapidly, and like I said, 20 to 40% of all changes occur in the initial conceptualization point of a project. But as you change requirements later on, you're going to have greater impact. It could stop the work that you're currently working on a system. You would have to go down and redesign it. It's going to be more costly, more time-consuming, so taking it early on is a good thing. But that doesn't mean that changes are negative. Changes can be positive. It could be that the customer decides to scope the project to something significantly smaller, which would be wonderful. But some of the things that you can do is understanding these understanding why requirements change. You know, is it because there was a scope change? Is it because there was a cost change? Is it because we're having to fix something? Is it something the stakeholders said? Understanding why they do can help you to be prepared for them and better understand and maybe ask questions so that you can anticipate when and if it might happen. It's also important to set requirements to chill and freeze things. And we found with some companies externally, they don't use chill or freeze. They use chill or freeze, but not both. By chill, we mean only critical requirements can come through and make some changes. Freeze means absolutely no changes anytime. So I put a hold on it. I said, no more changes here. We're done. We're going to full production. But with the chill, it might be, okay, you've got a good point, and you can document why these things need to be done. So establishing that critical no change date is really important so that things don't kind of creep in and you don't start saying, oh, wouldn't it be nice to have this feature or this function. Improving the communication between the requirements engineers, thinking about front-loading. You know, what kind of things can we do up front in terms of linking everything, how we're going to test it, how we're going to verify, what are those critical functions and features that we must meet, and setting those and working through those should help limit having changes later on. And next slide. Going through quick card. So what are some of the efficiencies that we realized that can be done? And I know even with internally to a lot of companies, is avoiding these big requirements up front. Don't start up thinking, let me go through this entire documentation and work through everything. It can be very wasteful, not only in time and money and effort. If you can avoid that, but think about, okay, what are the critical things I need to do? Let's think about these critical features, functions of whatever system we're designing. How are we going to verify that we met and developed a system that has these critical requirements and features? And by allocating these resources up front, bringing in your stakeholders, your designers, your test engineers, making sure that you've got a sound verification and validation plan, and that you might be able to, you know, have a common database that you're using to manage and monitor all of these requirements and keep them effectively. What you'll find is that later on, you're not going to have as many changes, and you're going to have a more effective product, and it'll be done with less time and less effort. So you want to also be aware that there are requirement changes. They're going to occur. There will be additions and modifications. Understand why, but determine who owns them, who's going to make sure that you verify and validate them. And you want to also try to avoid those slowdown errors, as I mentioned before, where I'm just trying to go through copy, paste, let me just go through it. Really need to think about it. It's really easy for me to say, I'm doing a feature and it needs to have file, menu, open, save, whatever. I'm going to just copy it across all of them. And it's common to do that and then go, oops, now I have one error in one. I've got to go through and change them all. So those are some of the key takeaways that we have found with our literature. And what we found when we talked to external organizations, they too have found that they're trying to be going more agile, but it's become very hard for them. Software companies are really good at it, but it's much more difficult for large manufacturing companies to do that. So it sounds great to do agile prototyping and agile software development and spiral development. It's a little hard when you're developing cars and trains and airplanes and whatnot.